Hi everybody, I'm the greatest living inventor, and today we are doing my invention, Supervolcano Pharaoh's snake. Okay, so I'll write it down. Supervolcano Pharaohs. And we'll close the door so we have less noise. Pharaohs snake. Okay, Pharaoh's snake is some chemistry demonstration that we'll talk about. In general, I did this lecture before, like right now I finished it, and this is take 2 because it was so long. It was like almost 1 hour and a half. So it didn't record it because of technical limitations, so I'm doing it again. So I will hardly write anything, just the main things. Okay, so excuse me, I will take off my shirt, my top. And also another thing, this is a special celebrational invention because it's the first invention of my second book, okay, about inventions. Not my second book in general, but my second book about inventions, the official guide to saving the world again. So it's another invention, but it's a special invention. Okay, so containing a super eruption. Okay, this whole thing is against a super volcano. Containing a super eruption by showering it with rubber, which goes through vulcanization in the natural sulfur and heat and form cells. These restrain bigger and bigger particles in a snowball effect until the weight stops the eruption. Okay, so I mostly will read it and I will write only when I have to. The problem. Supervolcano is basically a volcano that is 1,000 times more powerful than a normal volcano. You can see here, I will give you the link, Volcanic Explosivity Index. You can see here that there is a logarithmic scale called VEI. Okay, Volcanic Explosivity Index. Which is also called VEI. Okay, so this means that each step in the ladder is 10 times bigger than the previous. Each volcano is measured in how much matter it spit out. Okay, so it's like the Richter scale. Each level is 10 times more. Yeah. So an example for a normal volcano is Mount St. Helens, recently in 1980, spitting out 1 cubed kilometer of lava and ash. Okay, an example for a supervolcano is the Yellowstone caldera 600,000 years ago, which is predicted to spit out 1,000 cubed kilometers of lava and ash. According to Toba catastrophe theory, the last supervolcano eruption, which was about 75,000 years ago, caused a global volcanic winter for a few years, so there was no sunlight for plants, so there was no food, and this killed almost all humans in the world. So you understand that in a supervolcano the volume is 1000 bigger than a normal volcano, but the damage is much worse. Okay, now I'm reading to you a solution that doesn't work. It's not mine and it's not a good solution. The best idea so far how to solve this came from NASA. They want to cool the magma chamber by drilling deep vertical holes into the ground near the magma chamber, the heat engine of the supervolcano, and pumping water in and out in a closed circuit. The water goes down in the rock tunnel that acts like a pipe in a radiator. I'm sorry that I'm not drawing this. You can see, I will give you a link in the description to a video of this. It doesn't work anyway. Okay. The best idea so far how to solve this came from NASA. They want to cool the magma chamber by drilling deep vertical holes into the ground near the magma chamber, the heat engine of the supervolcano, and pumping water in and out in a closed circuit. The water goes down in the rock tunnel that acts like a pipe in the radiator. Okay, radiator which cools the car. The tunnel passes next to the steaming magma chamber. The water heats up, and by doing this takes a little of the magma's heat. So eventually the magma will cool down. The water goes up to the surface where the steam is used to rotate turbines to make electricity. Okay, this is, you can see it in a video which is called NASA's 3.5 billion, not million with an M, billion with a B, $3.5 billion idea to save Earth from a supervolcano apocalypse in the YouTube of Tech Insider. So I will give you the link. This solution would have been ideal because it prevents the eruption in the first place and it gives us clean green energy, but it can't work because it has two problems. One, it's dangerous. If the hot lava inside will touch the water there in the tunnel, this will produce so much steam gas, which occupies a lot more volume than liquid water, that the magma chamber wall will explode, and by this you can trigger a supervolcano eruption. So we are trying to prevent a supervolcano, and you can actually trigger a supervolcano eruption like this. So problem number two, it's slow. If everything works fine, the process is so slow that they calculated it would take 1000 years until you can cool the magma to a safe level in this way. Okay, 1000 years. Okay, so now a solution that works, my solution. My solution borrows its name from a classic chemistry demonstration. This is what our final product will look like, but on a gargantuan scale. Of course, in our case, we don't need to supply the hot gas that this chemistry needs, that is ejected here, because the volcano ejects the material. We just need to find a way to contain it. Pharaoh's Serpent demonstration by NileRed. I heartily recommend that you turn off the volume. It shows terrible music for this video. Okay, so it's called Pharaoh's Snake demonstration by NileRed. Okay, so this is 10 pages that I have to go through, so excuse me for not writing each link. I will put the links in the description. So how do we contain and lock inside cells cells in quote unquote, such a huge amount of lava, molten rock, and volcanic ash, which is like glass, and gas, sulfur. My first thought was epoxy resin. This is because resin plus glass creates fiberglass, which is very strong. But the problem with this is that the epoxy resin doesn't glue in high temperature. Other kinds of materials are heat resistant but don't have the other required properties to make the cells of the snake. Ceramics are not flexible, and metals are expensive. They are also very heavy. So we cannot take a very large amount of them by airplanes and drop them from above. If we just lay down the material on the ground, it might burn, because then the material comes in touch with the extremely hot lava before it had a chance to cool down. The most practical material to use for suffocating the eruption is what we have in abundance there, the very same material that the volcano is spitting out. I am saying suffocating, okay, in a very physical sense, because if the weight falls back down instead of being shot to the sides in parabolas, after some time the force of pressure from above, the total weight of the snake, will be equal to the force of pressure from below, the pressure left in the magma chamber, and the eruption will stop. Okay, so I'm just drawing this. Okay, if this is how it looks like in Yellowstone, and here there is the volcano. Okay. Okay, this is the mouth of the volcano. It's called caldera. And this is down here. There is a magma chamber. Then normally the weight of the mountain, okay, presses on downwards. This is the weight. And this is the pressure. So when the pressure is so big that it's equal or bigger, if it's bigger, then it wins and it erupts. Okay, so it erupts outside. If it's bigger than the weight, then it erupts outside and it shoots to the sides. Okay, so what we are trying to do basically is to let me erase this word because it's I will draw this again. Okay, so a normal volcano is shooting the material outside to the sides and it flows. But what we are trying to do in this invention is to lock it inside the cells. Okay, and so these cells don't let it continue outside, and then they fall back and close together, all these cells, close this, and they are their weight together is stopping. Of course, there is also in this side, and they are gradually stopping the eruption. Okay, so we are stopping the eruption, and that's the snake. This is what we call the snake. Okay, after a while it falls down, so it's lying on the ground. Okay, so the most practical material to use for suffocating the eruption is what we have in abundance here. I'll touch the air condition with a stick. Sometimes it helps. Okay, it doesn't help, sorry. I tried. So I hope you don't suffer too much from the noise, sorry. The most practical material to use for suffocating the eruption is what we have in abundance there. The very same material that the volcano is spitting out. I'm saying suffocating in a very physical sense, because if the weight falls back down instead of being shot to the sides in parabolas, after some time the force of the pressure from above, the total weight of the snake, will be equal to the force of pressure from below, pressure left in the magma chamber, and the eruption will stop. The thing which stops the eruption from happening right now is that the weight of the rock above the magma chamber is pressing on it, and right now it's stronger than the force of the magma. But how do we convince the magma not to be shot to all sides, and instead to stay in this area and fall back to the supervolcano, onto the supervolcano? We use a positive feedback loop, like a snowball effect, by impacting the smallest pieces, the tiny rocks, which, if we can stop them, will together slow down and eventually stop, on average, the small rocks, which would stop the bigger and bigger rocks, and so on. So okay, so the tiny rocks block. We deal with the dust and the tiny stones, the tiny pebbles, but they stop the the medium rocks and or the small rocks, and the small rocks stop the medium rocks, and the medium rocks stop the big rocks, and so on. Okay, how do we stop the volcanic ash? So our main question now is, how do we stop the volcanic ash? How do we stop the volcanic ash? We use the smallest materials, the smallest stones. We use a material that is produced exactly in these conditions of heat plus sulfur gas, vulcanized rubber. Okay, so if we take rubber, liquid rubber, plus heat plus sulfur then what we get is vulcanized rubber. So this is exactly the process that we use. Can you see the black? Okay. We use a material that is produced exactly in these conditions of heat plus sulfur gas, vulcanized rubber. Rubber is light, so it can be dumped from airplanes and meet the ejected gases in such a height in the atmosphere that they cool down to the necessary temperature not to destroy the rubber. So it's heat, but it's not heat like when it's got out of the ground. By the way, vulcanized rubber was developed by Charles Goodyear. The tire company is named after him. Vulcanization of rubber, 12th standard, chemistry, science, CBSE board, home revise. Okay, so there is a nice video about vulcanization of rubber, which I will put in the links. Then, when it comes down, it's like a gentle net or mesh of fiberglass, which holds some of the little bigger particles, and they in turn, these little bigger particles in turn create a little stronger net or mesh that catches bigger particles, and so on. What happens when the liquid rubber touches the gas? What happens when the liquid rubber touches the gas? Okay, so we have the liquid rubber. We are throwing it from an airplane, and the hot gas, the sulfur gas, comes from below, from the supervolcano. What happens when they meet? First, sorry, I will drink something. Okay, 23 minutes, I need to hurry. Sorry. What happens when the liquid rubber touches the gas? First of all, it cannot fall to the side, because unlike a normal volcano, the supervolcano ejects material in a wide surface, in a very wide surface. So if the blob of rubber misses the rising patch of sulfur gas, it simply hits another one on the long way down from the height of an airplane to the ground. We already talked about why it doesn't burn, because by the time the sulfur gas gets to the high elevation, it cools down. Both the sulfur cools down, both by occupying more space, like an air conditioner cools, and also by the cold air in the heights. The higher you go, the colder it gets. What about turbulence? Sorry. There are definitely a lot of eddy currents, whirlpools, in the gas that arrives. It's not like an air hockey table with orderly uniformed holes that blow air. The way I imagine it, and forgive my disgusting imagery, is the Latin phrase vir prudens non contraventum mingit. A wise man does not urinate up against the wind. Okay, it's a phrase in Latin, which is a Latin phrase meaning don't go against the conventional wisdom, the prevailing opinion. But here I will consider it very literally. If you have an ununiform current of air blowing, okay, wind, and you throw drops of pee on it, as you might imagine, it all, or most of it anyway, comes back at you. So this also answers the question, what happens when drops of liquid meet a turbulent gas? It's not lost, okay, it comes back. What I think will happen is that small bands of rubber will form. Imagine it like a rubber band that you use in the office, that you cut with scissors, so instead of a closed circle, they are curved into a line. So a normal rubber band, and you cut it with the scissors and you open it, so it's like a line, but not a straight line. So they are curved, thin line, curved. So we have many lines like this between the hot ash particles, and this all sticks together, forming a substance like flexible fiberglass. In parentheses, rubber is like resin, but more durable in the heat, more durable to the heat, close parentheses. The turbulence works in our favor to provide the mixing, so as much surface area of the rubber is coming into contact with the gas and volcanic ash. Sorry. So there was a phone. So as much surface area of the rubber is coming into contact with the gas and volcanic ash. Here is a video where we learn, okay, so this video is called What Do Raindrops Really Look Like? By It's Okay to Be Smart. And I wrote, I think the name of this YouTube channel says a lot about our times, not good things. Okay, so it's called What Do Raindrops Really Look Like? I will put it in the description. By It's Okay to Be Smart. I think it's PBS. Okay, so here is a video where we learn that raindrops actually are not in the teardrop shape, but instead they form a parachute shape. Okay, so you should look in the video, but basically raindrops don't look like this. They look like this. Okay, this is a parachute shape. Okay, so it's not really a parachute, but it's like it functions like a parachute and sort of looks like a parachute. Here is a video where we learn that raindrops actually are not in the teardrop shape, but instead they form a parachute shape after they reach terminal velocity, which for our purposes is great because they catch more ash this way like a bag. Remember, the rubber is more viscous than the water, so I guess it can form larger parachutes. Okay, this after a while it breaks into tiny drops like this, and then they uniform into a big one like this. But in this is in water, but in rubber it will be bigger parachutes. Okay, so now active deployment, continuous airborne alert of rubber bombers. I'm sorry everything is hurried. It's just that I'm really trying to make this work, and above 1 hour it doesn't work. What time is it now? 30 minutes. So active deployment, continuous airborne alert of rubber bombers. Okay, let's see first what we cannot do. We cannot scale up the toy weapon rubber band gun from childhood. See this link in the photo titles the disintegrator, which is a rotary gun version. Okay, so we cannot use rubber band gun. You know what a rubber band gun is. You stretch a rubber band and it flies to your enemy. So because there is no easy way to revert rubber back to liquid form once it turned into a solid. At least that's what I gather from Wikipedia, natural rubber, and from the answers here. ResearchGate.net post, how can I depolymerize natural rubber into liquid form and maintain it in liquid even if it cooled down to room temperature. Cooled to room temperature. I will put the link in the description. Notice that the original question hints that you simply hit the rubber, but according to the answers, this is not true. As you can read here in Wikipedia, in tires of a car, tire recycling, and the section tire pyrolysis. As you can read here in Wikipedia about rubber tires, in parentheses, although they are already vulcanized, so maybe it's a little different, close parentheses. The way to recycle rubber is to heat them without any oxygen. But since we shoot the rubber onto the volcano in open air, there is oxygen in the air, so this will not work. So we look at solutions from the firefighting department, because they have a similar mission of spraying liquid over a specific area. Water cannons will not work, because even with water, which is not viscous, it can only reach dozens of meters, which is too low. Okay, so water cannon is not good. You can see in Wikipedia water cannon. So what we need is another tool from the arsenal of firefighters, which is firefighting airplanes, called water bombers. Okay, so we are doing the same, but instead of water bombers, we put liquid rubber in this. So you should look in Wikipedia about water bombers, aerial firefighting, and the section is water bombers. I will put a link in the description of the video. So, so what we need is another tool from the arsenal of firefighters, which is firefighting airplanes, called water bombers. So we do carpet bombing, but with rubber. but in our case we fill them with liquid rubber. So I'm sorry, for ease of storage we can pack it in rubber bags and only slice the bag open when it's deployed over the target. My suggestion is that we will maintain a continuous airborne alert like in Operation Chrome Dome. Okay, Operation Chrome Dome. My suggestion is that we will maintain a continuous airborne alert, that they are in the air all the time, like in Operation Chrome Dome, when American bombers were flying all the time with hydrogen bombs ready to drop on the Soviet Union. You can see in Wikipedia. By the way, if you like movies, in the middle of that operation period, 2 films were made: Dr. Strangelove, highly recommended, and Failsafe, which I hope to watch someday. But this time it will not be used to kill all mankind, but to save all mankind. Okay, so another option is passive deployment. Okay, hot air balloons. Hot air balloons or drogue parachutes. Raising capsules. Okay, so this is basically, imagine that you have this is one option, this is another option. So imagine that you have a capsule coming from space or something. It has parachutes, okay? Drag parachutes, they slow it down so it comes slower. And if you take, and there is a capsule that is hanging there, okay? So if you do something in reverse, okay, you have a capsule, like this sphere is a capsule, and it's attached with the lines, with the strings, to like a sail here, a parachute. Okay, so if there is a wind coming from down to up, then it will raise this parachute with the capsule to the air. Okay, so this is the main idea here. Raising capsules. This is the capsule. So it's raising on the hot wind of the gas that is coming from the supervolcano. Okay. What if the volcanic ash grounds the airplanes? In Wikipedia you can look volcanic ash and aviation safety. As you can read at the end, it interrupted an airplane that was 11 kilometers high. Of course, the airplanes should try to reach the ash from upwind and try to use the momentum of the rubber package to gain safe distance. The rubber will keep the original trajectory until it hits the target. But still, what can we do if we missed our first chance to contain the ash? We need to use what's already there to do the job for us. Okay, this wind is already there. We need to use what's already there to do the job for us. Since gas is lighter than liquid and solid, I assume what will get out first from the volcano is the very hot and corrosive volcanic gas. And you can see in Wikipedia, volcanic gas. I will put a link. So if we can catch it and ride it, we could prepare in advance closed and heat insulated parcels of rubber. Okay, so inside here there is rubber. This is the capsules that will be lifted by the upgoing currents of sulfur gas, and then we need to plan how at the right moment the parcels will open and drain rubber. What is the toughest fabric we can use for the sail for this? Okay, so here I'm writing a few options. I will erase this. What time is it? Okay, 42 minutes. I need to hurry. So now we are talking only about the second option. This is until the end of the lecture. We are talking about the parachute. This. Not so much parachutes as sails that go from the ground to upwards and then open, and the rubber falls on the volcano. Okay, so this is the raising capsules. This. What is the toughest fabric that we can use for the sail? Okay, so sail, the blanket, the parachute, the fabric. One option is polybenzimidazole, midazole, fiber. Okay, this is called PBI. This, I guess, is the best alternative. This is the stuff that they use in astronauts' suits. See picture in Wikipedia, replica Apollo spacesuit in the above link. Okay, so if you look in Wikipedia and this. Dynamic flame test by PBI Performance Products. I put a YouTube video. Okay, another option is ZX. Non-toxic replacement of asbestos. And another option, which I think is the simplest alternative and can be used and can be made with all sorts of materials, some are very common like silica, is ceramic impregnated fabric. Okay, I'm sorry it's all rushed, but I have to record it in less than an hour. Okay, so you can look at this in Wikipedia also. Each of them you can look in Wikipedia. I'm putting the link in the description. Our design needs to be something between a drogue parachute and a hot air balloon. Okay, I'm putting a link to drogue parachute, which is slowing something down. The first gush of air is very strong and sudden, like drogue parachute. But afterwards, we need the blanket that is spread on the ground at first for maximizing the chance of catching the gas eruption to take the shape of a hot air balloon, like a bag or parachute, so that the hot gas will not escape. So I think the most logical shape from symmetry considerations would be a sphere made of a lightweight but strong material, one of these, tied underneath a blanket from the toughest material we can get, which covers it, and it's, I'm sorry, this is for the blanket. And so I think the most logical shape from symmetry conditions would be a sphere. What is hanging is a sphere made from a lightweight but strong material, tied underneath a blanket from this, from the toughest material we can get, which covers it and is spread on the ground. So at the beginning it's on the ground, and then it catches the geyser, the gas that's coming up, and flies. The ideal shape of the blanket will be a sphere, but we need these tiles to cover the whole area. So to minimize the chance that the geyser of sulfur will erupt between the blankets. So I recommend hexagonal shaped blankets with small weights tied along the perimeter. Okay, so I recommend that it will be hexagonal. And it will have small weights. Okay, each of these is a weight that when this is flying, it closes around the gas, the hot gas that is coming, so it covers it, and it the weights pull it down. Okay, like a cover. So the blanket will later take the shape of a sail or a balloon. The sphere capsule can be made of aluminum, which is strong and light metal. Okay, so tied to this is a sphere. Okay, and later the sphere, after this is flying, the sphere will be below. Okay, so after this this thing is flying, the sphere is below. The sphere capsule can be made of aluminum, which is strong and light metal. I think it can be designed to explode once it reaches a certain optimal altitude, using the pressure change of the air inside and outside. On the ground we have 1 atmosphere of pressure. In 10 kilometers we have less than 30% of that, 30% of that. We need to consider the expansion of the air inside the capsule in the beginning, caused by the thermal expansion of the air from the heat of the gas coming out of the volcano. So instead of ordinary air, we can use in the capsule a noble gas that wouldn't expand so much from the heat. We are talking now on how the capsule will be made. Wouldn't expand so much from the heat, like argon or krypton or xenon and so on. What time is it? 51 minutes. I need to hurry. So I'm erasing this. Okay, so now we are only talking about the capsule. And this is the capsule. And we make it from okay, so inside we have the rubber. Liquid rubber, and we also have the noble gas. Which can be, I told you, argon, or krypton, or xenon, okay, and so on. To insulate the hard protective shield, heat conducting aluminum, okay, this is aluminum, from the sensitive to heat cargo, the liquid rubber, because we don't want it to get burnt or something in the beginning. We want it to stay liquid as much as possible and drain afterward. I suggest the capsule will be a sphere within a sphere. Okay, so we have another sphere. Okay, let's do this sphere in red because this one is getting hot from the outside, but it's insulated. It's not touching the sphere in the inside. Okay, this is inner sphere. And this is outer sphere. and they are not touching each other. To insulate the hard protective shield, heat conducting aluminum, from the sensitive to heat cargo, liquid rubber, I suggest the capsule will be a sphere within a sphere. The rubber will be inside, the rubber will be inside the inner sphere. I suggest the capsule will be a sphere within a sphere. Okay, sphere within a sphere. The rubber will be inside the inner sphere. And between the two spheres, we use a material which insulates heat in high temperatures. So now I'm quoting an article that I will put a link to. Review of high temperature thermal insulation materials by Maria Tichanik's Quachian, Joanna Wilk, and Powell Gill. Okay, I will put a link. It's in Sci-Hub. In the article, they also say, as far as fibrous, fibrous means a material with holes, like Swiss cheese. As far as fibrous materials are concerned, the alumina-based insulation materials in high temperature space shuttle applications, and they continue. This is the quote. And you can read in Wikipedia too that alumina aerogels, okay, so alumina aerogels, and it's like a block that has tiny microscopic holes. Okay, it's like it's full of air, but in the microscopic, it's called solid smoke. Okay, aerogels are called solid smoke. Because they are so lightweight, but they are very strong. There is a picture, if you look in aerogels in Wikipedia, there is if they are made from like tough material like silica or metal oxide, they can carry, you can put something like this, a block of aerogel that weighs like 2 grams, and it will hold a big block of construction from stone that is that weighs 2.5 kilograms. Okay, so it's very tough but very lightweight, and it's very insulating. It's insulating heat, so it's good for us. So alumina aerogels made with aluminum oxide are also being considered by NASA for capturing hypervelocity particles. Okay, this is from Wikipedia in aerogel in the section metal oxide. Okay, so I think since we want between the inner sphere and the outer sphere both components, okay, we put blocks of this here. Okay, so we put a block here, a block here. And between them, we also put a noble gas. So just like we have here a noble gas, we also have here between the blocks noble gas. So this also explodes when the time comes, when it's in the altitude that we want. But also these blocks make sure that it doesn't, the inner sphere doesn't touch the outer sphere, so it's isolated. So I think since we want between the inner sphere and the outer sphere both components, the green and the blue, the insulating aerogel and the popping gas, we should make room for both of them. For example, blocks of aerogel evenly spaced all around, and between them, between them, space for the noble gas. So the inner sphere stands on the aerogel blocks, but the inner sphere is still surrounded evenly on all sides by the noble gas. Okay, so I hope it was clear. Sorry it was rushed, and I will see you in my next invention. Thank you very much. Bye-bye.